Good afternoon everyone. Today we are going to see fuzzy logic control part 1. The outline of this lecture will be first introduction to fuzzy logic control, then we will be seeing Mamdani type of fuzzy logic controller, and in that one example of a two-wheel mobile robot for trajectory tracking task, and then finally we conclude our talk or lecture with Lyapunov function based fuzzy control. Now coming to fuzzy logic control introduction. Fuzzy logic controller is an approach to represent human like thinking in a control system, and it can be designed to imitate human deductive thinking to deduce conclusions, to infer conclusions from the past experiences. We can see when fuzzy controller can be applied. It can be applied when there is a problem associated with the classical control strategy, such as unavailability of data, parameter variation problem, highly complex plans and inaccurate model. During these circumstances, one can apply fuzzy logic controller in order to get good results. Now coming to the types of fuzzy controller, there are two types. One is called Mamdani type fuzzy controller. It is basically a direct adaptive control strategy that has been designed directly based on the fuzzy rule base. Fuzzy rule base is nothing but a set of fuzzy rules. These fuzzy rules can be derived or designed based on intuition or based on Lyapunov function candidate. Now the another type of fuzzy controller is Takagi Sugino type fuzzy logic controller. It is an indirect adaptive type controller in which the system to be controlled has to be identified in terms of a TS fuzzy model, and based on this TS fuzzy model the controller is designed for the system. Now let us see about Mamdani type fuzzy controller, which is the first type in our lecture today. So the block diagram of Mamdani type fuzzy controller is that first it has Fuzzification process where the crisp input has been converted into a fuzzy output. A crisp value is converted into a fuzzy value through Fuzzification, which is done by a fuzzifier, which is done basically by involving membership functions, because membership functions are the one that converts a crisp value into a fuzzy value, and then the fuzzy output from a fuzzifier goes to fuzzy inference system, which is basically involves rule base, a set of rules, and the inference engine or inference mechanism chooses which rule it is, or to get the consequence of each rule we can use the minimum composition to get the consequence of each rule, and this consequence of each rule has been combined to form the output distribution. From the output distribution we can go for defuzzification, that is the output of this fuzzy inference system goes to defuzzifier, where defuzzification happens, which means a fuzzy input has been converted to crisp output, which is helpful for the control action of a system or a plant. So there are three fundamental blocks: fuzzifier meant for fuzzification, rule base, associated with rule base is the fuzzy inference system, and the defuzzifier meant for defuzzification, converting fuzzy to crisp, because in the real world we need a crisp data. That is why crisp input is given as input to the fuzzy logic controller, so that we get a crisp output as a control signal for the plant which has to be controlled. Now here is the flow chart of fuzzy Mamdani type controller. It shows that there is a plant whose current position or actual position has been sensed by a sensor. That value has been given to fuzzy inference for fuzzification, which converts it into a fuzzy value, and there is a fuzzy inference mechanism which produces the output in terms of fuzzy, so that the fuzzy value has been converted into a crisp value by defuzzification. There are two popular methods in defuzzification, it is weighted average and center of gravity approach. And then the crisp output of the defuzzification block goes to the actuator, and the actuator actuates the plant. Accordingly, we get a response that has been sensed by the sensor, and the process is iterative in nature. And you can see here in Mamdani type fuzzy controller, this fuzzy inference mechanism is having a fuzzy rule base with output state variable also represented as linguistic variable. That means, we have if x1 is a1 and x2 is a2, then y2 is b1. So, in this way the output is also represented by a linguistic variable, directly comes as a linguistic variable. That is the salient feature here. Whereas, in terms of TS fuzzy controller, the output is given by an expression, not directly as a linguistic variable. It can be derived, the output can be derived in terms of an expression in TS fuzzy controller. Now, let us talk about the fuzzification. Here the crisp value is converted into a fuzzy value by fuzzification process. Let us consider two input states E and delta E are the two input states, precisely they are the input variables, and they are converted into fuzzy sets using triangular membership functions. Here you can see in the schematic here, rule 1, the membership function value for E and membership value function for delta E. So, based on the crisp value of E, we get a corresponding membership function value 0.8 in rule 1. Similarly, the crisp input of delta E in its membership function gives 0.3 corresponding to the crisp value delta E. It gets 0.3, and you can take here. Okay. So, the minimum of this will give the output membership function value. This is u. That means, these two values are correlated by AND function, so that we get the minimum, that is the output of this rule. Similarly, for rule 2, we have the crisp value of E considered with the fuzzy value 0.7. Accordingly, the crisp value of delta E has the value fuzzy value 0.8 by the membership functions. Here it is triangular membership functions. This way of converting the crisp value of the states into fuzzy values is called fuzzification approach. And as I mentioned you that how we are getting the output membership function values, that is based on your AND operations of the membership function values or the fuzzy values. Next, we move on to the fuzzy inference mechanism. It chooses a suitable rule from the rule base. It deals directly with the rule base. Rule base is nothing but a set of rules, and we are going to see how many rules a system has if it has n dimension state space. Okay. So, now coming to the fuzzy inference mechanism, a logical it establishes a logical connection between the input and the output fuzzy sets. It performs operations on rules as a decision making unit. Fuzzy inference system performs operations on rules as a decision making unit. It establishes the rule strength by combining the fuzzified inputs according to fuzzy rules. Again, it establishes the rule strength by combining the fuzzified inputs according to the fuzzy rules, rule 1, rule 2, rule 3, because rule 1, rule 2, rule 3 definitely are going to have different fuzzy strength, different rule strengths. Then the consequences are obtained based on combining the rule strength and the output membership functions. Okay. Now, the fuzzy inference mechanism continued that what will happen with these consequences. By combining the consequence of each rule, the output distribution is obtained. That is why from rule 1 to rule 10 or rule 1 to rule 5, there are 5 rules, 10 rules, 25 rules. Each rule has been operated or coming under the operation of composition based on OR function. So, the maximum function has been applied with the membership functions of the output of each or the consequence of each rule. Next, the final block is defuzzifier, where defuzzification process happens. It converts a fuzzy value to a crisp value using defuzzification methods such as center of gravity approach or weighted average approach. Any one of these approaches is generally used to convert a fuzzy value into a crisp value, so that the crisp value is the output of your fuzzy controller block. That block, that value is called the control input signal to the plant. Now, let us take an example which is basically a Mamdani type fuzzy controller for a 2-wheel differential drive mobile robot. This is basically example 1, it is not 2, it is 1. So, the task is to track given trajectories, say circular trajectories or Lissajous trajectories. Through Mamdani fuzzy controller, we need to make this robotic system to track these type of trajectories, circular trajectory and Lissajous pattern trajectory. Let us see. So, the steps involved in order to perform this task through fuzzy Mamdani type controller involves give the desired circular trajectory in terms of xd and yd, because it is a planar circular trajectory. So, xd yd, if it is 3D then xd yd zd, then give initial position of the robot where it is placed initially, and then we have the for loop to take forward. First, find the desired orientation angle using the current position of the robotic system. Say for example, this is the situation and the robot is here, which is x, y, and here is theta, which is orientation. The orientation is obtained with respect to the global frame. The robot frame, body frame is compared with the global frame. So, G represents the global frame or represents the robot frame, which is in the center of mass of the chassis or of the body of the mobile robot. So, here we have x, y and theta of the center of mass of this mobile robot. Now, the task is to reach here and track these waypoints of a circle. Then come back here. Now, as a first step we need to find the desired orientation, because we have xd yd of all the waypoints and we also need the orientation to be given as input to this robotic system, because the robot has to track in this fashion. Here are the two wheels. So, in this fashion, and it continues here. Okay. So, if the orientation is not taken into account, it will not trace the trajectory of a circular path properly, which means that the center of the mass will be, the position will be tracked because of x d y d. If we do not give x d and theta d, if we do not give theta d, this circular trajectory will be tracked like this. Let us say so, you can see where the wheels are. The wheels should be facing the forward direction, as in this case. That is why we need to specify the theta d as well. Then only that will be taken into account by the controller, and we can have the two wheel robotic system to track the circular trajectory in a proper orientation. Here the orientation suffers, whereas here the orientation is proper. Next, find the error in distance, say E d, which is x d minus x. Likewise, find the error in orientation, which is E theta, which is theta d minus theta. And then find the input membership functions for the input variables. What are the input variables here? E d and E theta. So, find the membership functions for the input variables, because the membership functions are the ones that will give the values meant for fuzzification as well as for defuzzification. Okay. The membership functions converts the crisp values into fuzzy values, and these fuzzy values are utilized in defuzzification steps as well. Then finally, use the rule base to find the outputs. Rule base is the building blocks in fuzzy controller. Then do the numerical integration in order to obtain the actual position of the center of mass of the robotic system, x and y, as well as the orientation, and end of the loop, and this loop continues as we come to the end of the trajectory point. You start here and end in the same point, so that the robotic system completes its circular path. So, the detailed explanation starts now. Before that, we need to have the kinematic model of this two wheel differential drive robotic system. First of all, the configuration of the mobile robot is characterized by the position x y as well as the orientation in a Cartesian coordinate system, capital C here. Now, let us see the kinematic model is given by x dot equal to v cos theta and y dot equal to v sin theta and theta dot equal to the angular velocity of the body, which is given by r by 2b into theta r dot minus theta l dot, where x dot is the velocity along the x axis and y dot is the velocity along y axis of a robotic system, and theta dot is the angular velocity of the mobile robot. Then theta r dot and theta l dot are nothing but the right and left wheel angular velocities respectively, and r is the radius of the wheels and 2b is the distance between the centers of the wheels. this is a mobile robot, the wheel, and this distance is 2b. Now, the kinematic model in discrete domain is given by x k plus 1 equal to x k plus v k cos of theta k into delta t, for the sampling period capital T you can specify. Similarly, for y k plus 1 and next instant of the orientation value theta. Okay, so, since it is discrete form, definitely sampling time plays a vital role in taking to the next sampling instant. Now, coming to the design of fuzzy logic controller based on Mamdani type has this form: give the input as distance error and angular error, theta E theta and E d, and the output of the fuzzy controller will give you the linear velocity and angular velocity of the robotic system. Linear velocity is represented by x dot v dot and angular velocity is represented by omega of the robot body, and there are certain rules forming the rule base meant for the fuzzy inference. Okay. So, now let us see the input variables to this problem are distance error E d given by x d minus x whole square plus y d minus y whole square root of it. Similarly, orientation error is given by theta d minus actual orientation, where theta d is given as tan inverse of y d minus y by x d minus x, where y d and x d are the desired circular trajectory positions for this robotic system. Now, coming to the input membership functions, triangular membership functions are considered for fuzzification process for this particular problem, trajectory tracking problem of the two-wheel mobile robot. Since the variable d, which is the distance, is positioned in the universe of discourse 0 to 20 centimeter, which is defined by membership functions. So, we consider 5 linguistic variables associated with the distance: 0 distance, small distance, medium distance, long distance, very long distance. So, 5 linguistic variables associated with the input variable or fuzzy variable d towards the distance. Similarly, the angular fuzzy linguistic variables are 0 angle, positive angle, very positive angle, negative angle and very negative angle VNA, and it is the angular value is positioned in the universe of discourse within the range minus 180 degree to plus 180 degree. Now, let us talk about the output membership functions. The linear velocity and angular velocity are the output variables, and again we considered here 5 membership functions corresponding to the 5 fuzzy variables associated with the fuzzy linguistic variables associated with the output. So, let us consider 0 speed, slow speed, medium speed, fast speed, very fast speed, 5 linguistic variables associated with the output fuzzy variable. So, we consider a simplest straight line membership functions for this 5 fuzzy linguistic variables associated with the output. Likewise, for the angular velocity output variable, we also consider 5 fuzzy linguistic variables such as 0 angular velocity, medium positive angular velocity, medium negative angular velocity, large positive angular velocity and large negative angular velocity. Accordingly, we have 5 straight line membership functions for this angular velocity output variable. Now we form the rules. Now how many number of rules? In general, in fuzzy logic controller, the number of rules is given by an expression q power n, where let us consider an n dimensional state space where the dimension here is n, and we have q number of fuzzy zones associated with the states. So, the total number of rules is given by R equal to q power n, fuzzy zone power number of states. So, number of states in our case is 5, in our case is 2, and the fuzzy zones in our study is 5. So, 5 power 2 equal to 25 rules. Accordingly, we have developed 25 rules. Input is ZD, 0 distance, and input theta d, theta E theta is 0 angle. So, the output is 0 for velocity, angular linear velocity. Similarly, 0 distance, similarly the output angular velocity is 0 angular velocity. Likewise, we go up to framing 25 rules, constructing the rule base. Now, coming to the defuzzification, we have utilized the center of gravity approach, which is given by the output value, precisely the crisp value of the output, say Z crisp, is given by the integration of mu of Z into Z multiplied by Z into dZ divided by integral mu of Z dZ, where Z crisp is the output value, crisp output value obtained by defuzzification, and mu of C is the membership function of the fuzzy set at a particular value of Z. Okay, so this is corresponding to so the Y star is called the crisp value, in this case Z crisp. So, this is the combined or the distribution of the output. From this distribution we get the crisp value by center of gravity method by this expression. So, the results obtained by this implementation of Mamdani fuzzy controller to a 2-wheel mobile robot gives you this type of well accurate trajectory tracking performance, and this plot shows here the error plot considering both the distance error as well as the orientation error converging precisely, and we have finally the angular velocities and the linear velocities associated with the robotic system. We can see now the demo, experimental demo of the robotic system in tracking the system. So, we can see here this is the demo of the mobile robot tracking a circular path obtained or controlled by this developed fuzzy controller. Next, we have a Lissajous pattern tracked by this robotic system through this Mamdani fuzzy controller, and then this. Now, coming to the final portion of today's lecture is being the stability analysis of a fuzzy logic controller system controller using Lyapunov function. So, now consider we can understand this topic based on an example considering a scalar nonlinear system given by x dot equal to minus x cube plus u. So, the objective of this problem is to design a fuzzy logic controller so that the plant is stabilized around the origin x equal to 0. The solution to this problem starts with selecting a Leibniz function candidate, say v equal to half x square. So, v dot becomes x dot, substituting the value of x dot here, we have v dot being minus x power 4 plus x u. We know that the Leibniz function candidate is a positive definite function, scalar positive definite function. So, v dot we want to be negative definite, so that the system is stable. So, we define two rules that will make v dot negative. So, we consider if, as per the expression of v dot, if x is negative then u is positive, if x is positive then u is negative. So, accordingly we have the control input as per the condition of x, x is positive then u is negative, and x is negative u is positive. So, based on this condition of u, we have the system response of this one dimensional system converging smoothly, and we can observe the stability of the system. So, coming to the concluding part of this talk, this lecture, we can say that we have introduced a fuzzy logic controller. In that there are two types, Mamdani type and TS fuzzy model type. The Mamdani type, which is a direct adaptive control type, we have seen this fundamentals of Mamdani type, the basic strategy of this Mamdani type fuzzy controller with an example of two-wheel mobile robot tracking a circular trajectory as well as Lissajous pattern, and then we have seen also the stability analysis of a fuzzy controller using a simple one dimensional nonlinear system. Thank you so much for your patience. In the next class we will be seeing the TS fuzzy model along with fuzzy PI PD controllers. Thank you very much.